Today we're going to be simplifying radicals. So a radical is the root of a number. So we think about lots of different square roots. You've probably had some experience with that. Square root of 4 is 2. Cubed root of 8 is 2 times 2 times 2 equals 8. So cubed root of 8 is 2. Numbers whose square root is an integer are called perfect squares, which is really nice. You end up with the square root of 4 equals 2, square root of 25 is 5. Those are perfect squares. But for numbers and monomials that are not perfect squares, we can simplify the radical. And that's what we're going to be talking about today. A radical is in its simplest form. That's going to be the most important thing when none of the numbers under the radical are perfect squares anymore. Let's get to some examples. So the square root of 169 is, we know that 13 times 13 equals 169. So to simplify this one, it is just the number 13. But 32 is not a perfect square. It is something that we aren't able to just magically create a perfect square from that. But we do know there are perfect squares in there. So what I was thinking about was I see a perfect square if we cut that in half. So the square root of 32 is the same thing as the square root of 16 times 2. 16 times 2 is 32. So square root of 16 times 2 would be the same thing. We can then split that into the square root of 16 times the square root of 2. Square root of 2, that's as far as we can go. 2 is not a perfect square. But the square root of 16 is 4, because 4 times 4 is 16. So our most simplified form here would be 4 root 2. So to simplify a radical, use the following steps. And this is something you should probably have in your notebook somewhere. Factor out any perfect squares from the number. So we just did it with 16. We saw 32. We knew we could get 16 out of that, and 16 is a perfect square. Square root of 16 is a perfect square of 4. Separate perfect squares and non-perfect squares into separate radicals, and then simplify those perfect squares. If you want to have it written down in some way, this is definitely a great order to have. So the square root of 50. This is not a perfect square, but we do see perfect squares in it. If you're thinking to yourself, okay, 50, I know that it could be multiplied by 10 times 5 is 50, but there's no perfect squares there. What about cutting it in half? 25 times 2, boom, there we have one. We know that the square root of 25 times 2 is 50. It does equal the square root of 50. Square root of 25 times the square root of 2 would leave us with 5 times the square root of 2, and that would be its most simplified form. Example number 1, let's simplify 450 as a square root. This one again, 45 times 10, you got to just start using those like multiplication tables in your head and what's going to work out. Does 25 go into that? Yeah, probably, but I happen to know that 225 is a perfect square. So, square root, oof, tough handwriting there, 225 times 2. And the square root of 225, 15 times 15 equals 225. So we're going to need to start to get to know our perfect squares. Square root of 225 is 15 root 2. This would be the most simplified version of this right here. Now there's more ways we can do this, so let's take a look at those in another example. Variables with exponents can also be perfect squares. Any variable that is, oh, sorry, going to go back here. I did want to talk about, let's just say that you didn't know that the square root of 225 was 15 off the top of your head, and you went a different direction. Let's say you went with 25 times 18, because you saw 450, and you thought 25 would definitely go into that. Took your calculator and did 450 divided by 25, and you got 18. This also, we can get to the same response. We can get to that same area. So square root of 25, that's good news. We also see 18 here. There is a perfect square in here as well, because we know that the square root of 25 times the square root of 9 times the square root of 2 is going to help us out as well. So here we have square root of 25 times square root of 9 times square root of 2. Square root of 25 is 5, square root of 9 is 3, and the square root of root 2 stays at root 2. 5 times 3 is 15. So this step over here took a little bit longer, but we still ended up in the same location. Both are good ways to get to the answer. Now, moving on to variable with exponents can also be perfect squares. Any variable with an even exponent is a perfect square by nature. So to find the square root of an exponent, divide the power by 2. Here, we have the square root of x to the 8th power equaling x to the 4th power. One way that I like to think about this is we know that 5 squared equals 25, and we know the square root of 25 equals 5. So if we were to say something like the square root of 5 squared, okay, what's happening here? We are going to eventually square root it, and it's being squared. Do you hear what I'm saying? Squared, square rooted, squared, square rooted. So this equals 5. In this situation, we don't know what the variable is yet. But if we're square rooting something, we can cut this in half. 5 here would be to the 1st power, which equals 5. Here, we're cutting it and dividing it by 2. Let's look at another example. Example 2. Simplify the square root of m to the 15th power. All right, that's an odd number, but that's all right. We know that m to the 15th power, I'm not going to do all these, is m times m times m times m times m, all those things. But we also know that the square root of m to the 14th power is being multiplied by m. Now I've created for myself an even number, and this is still true to what we started with. M to the 14th power is being square rooted. So I can simplify that and keep my square root of m, where I don't know what that is yet and I haven't been able to manipulate that yet, but I can still simplify this into m to the 7th power times the square root of m. Now, why are we going to do that? Why do we need that? Anytime we can simplify anything, it's going to make it easier. Think about doing multi-step equations. If we don't combine like terms, it's going to make our process harder. We always want to be able to simplify when we can, and we want to find even numbers in our example. Example 3. Here we have two variables. We have a to the power of 9 and b to the 14th power. I see an even number with b, and that's great news. A to the 9th power. Well, I'm not going to be able to cut that in half, but I do know that a to the 8th power times a times b to the 14th power, I'm going to be able to simplify those. Let's separate them even further. A to the 8th power times the square root of a times the square root of b to the 14th power. I'll be able to move two of these outside. If I cut a to the 8th power in half, I'm left with a to the 4th power. I've got b to the 7th power are being multiplied by the square root of a. And I've been able to move a lot of that outside of the square root, which is going to give me a lot more freedom going forward. Now, what if they're mixed? Here we have the square root of 288 times x to the 13th power times y to the 5th power. All right, let's see what we can do here. I don't know what you're going to think is the simplest one. Right away, my brain thinks about 288. If I cut that in half, that's 144. And I know that's a perfect square. So I'm just going to start with that. 144 times 2. X to the 13th power times, I want to make this an even number, x to the 12th times x times y to the 4th power times y. This looks a lot more complicated right now, but I've taken this, I've separated each of them into parts that I can simplify further. Boy, that's a terrible circle job. Okay, what do I do next? Well, I know that the square root of 144 is 12. Square root of 2, I have to keep. X to the 12th power, that's going to be x to the 6th power. Square root of x, I have to keep. Square root of x to the y to the 4th power, it's going to be y to the 2nd power. And I have to keep square root of y. Now this is a jumbled mess. You're going to need to make sure that you're careful about keeping yourself organized, keeping the square roots together and the non-square roots together. So let's change the color up here. On the outside, I have 12 times x to the 6th power times y to the 2nd power, and inside my parentheses, I'm left with 2x, y. That is the most simplified version of that. All right. Practice more in class.